All right, so let's talk about hybrid orbitals. In the last part one, we're talking about how hybrid orbitals are considered to be these combination of electron clouds so that there is some sort of bond to be formed. So the word hybrid means combination, and orbitals, obviously, we're talking about the electron shells, the electron clouds. And what happens is that the central atom is going to have some sort of overlap with those terminal atoms on the side. And what you're going to need to know is the names of 3 accepted types of hybrids and their bond angles that come with them. And so let's go ahead and jump in right to those. So the ones you have to know here are going to be charge clouds around the central atom. Earlier we defined as a charge cloud as an area where electrons are found. These charge clouds are basically these areas where electrons are going to be bonded to the central atom. So let's take a look at the first one. What if I have 2 charge clouds? In other words, a linear structure. In this case, because we have a linear structure, we're going to find out that the hybridization, in other words, the overlap from those 2 terminal atoms, are going to include the S and the P. That's going to be called a sp hybrid orbital, and it has an ideal angle of 180. And so in the last example, we were talking about carbon dioxide, or CO2. CO2 is carbon in the middle, O's on their side. We have a 180, and that's going to be considered an S and a P. And we'll talk a little bit about why it's an S and a P later. Second one's going to be a 3. So 3 charge clouds around it. That can include, obviously, a lone pair, and that includes also atoms. So you can have 3 atoms, or you can have 2 atoms and a lone pair. In this case, we're going to have 2 P's and 1 S. Notice carefully, the S's don't really add up, but if you think about it for a second, the P's, we have 2P, we have 6 electrons in each P, so we have Px, Py, Pz. And in this case, the angles are going to be 120. So if you think about that example, that's going to give you a 120-degree angle for that, ideally, right? And the last one is a 4, is we have 4 charge clouds, like, for example, a tetrahedral shape. In this case, we're going to have a situation where we're going to have 3 P's, and then it's going to be about 109.5. And that's going to give you an sp3. Now, 3 coming out from the 3 P orbitals that come with it. So again, memorize this. Make sure you understand that. That's 180, 120, and 109.5. So let's talk about this example here for C2H4. This one has, we're going to take a look at the CH3 on the left. We're going to take a look at the CH3 on the right. And in this case, the carbon has 3 charge clouds. This carbon has 1, 2, and 3. And then this carbon here has 1, 2, and 3. Because of that, each carbon has 3 charged clouds. In other words, is an sp2 hybrid. Now, the best example I like to give here, if it has 3 things attached to that, if you add the 1 here and then the 2, that gives you 3. If you go back to this example here, if you have 2 things attached to that, you add a 1 and a 1, that gives you sp. If you have 3 things, it's 1, 1, 1, which is 1 plus 2 gives you 3. And then for the sp3, that gives you 1, 1, 1, 1, that gives you a 4. So, interesting, a little shortcut way of doing it. Now, again, the angle here for a sp2 hybrid is going to be 120. So if you multiply 120 times 3, that gives you 360 right here. And that also gives you 360. So a double bond is a little bit different. A double bond is considered to be, it's made of 2 things, one called a sigma bond and the other one called a pi bond. So the sigma bond is going to be between the S. So we're going to call this one S for sigma, pi for the double bond. And what you're going to have here is, well, technically it's the p orbitals, not the double, excuse me on that. And then when you add them together, you're going to get a double bond with a sigma and a pi. Now the p orbitals are going to look like these, kind of like peanut shapes or balloons. And then the sp2 orbitals that we have here earlier is going to overlap between each of the carbons. So you're going to have the p's overlapping, and then you're going to have 3 of these sp2s. So, in a nutshell, what you're really looking for is these sp2 connections that you see right here, because of the fact that there's a double bond in play. Okay, so the sp2 is going to be considered from that sigma bond. Now, in a sigma bond, in a single bond, you have sigma bonds, and you're able to spin around on the axis, while double bond, you're going to have a pi bond, which prevents it from spinning. So normally a sigma bond, you're going to have this kind of like swirl around, but with the double bond, you're going to have the pi bond, which is going to block it. And so that's why you kind of get this kind of weird configuration, because of the fact that you got that pi bond in. So this is a little bit on isomers, just talking a little bit about the different ways in which you can write down. So sometimes when we write these carbons, you can write them out as cis or trans. So cis meaning that the carbons are on the same side, and trans meaning that the carbons are on the opposite sides. And so in this case, you have cis-2-butane. The carbon chain is going to be here, and then the trans meaning that you're writing them on the outside. So that's another thing. If you see this cis-2, that will tell you exactly where the carbon is actually going to be located. All right, for triple bonds, we actually have two charge clouds. So we have hydrogen here and carbon here, and these are considered to be sp orbitals, or 180, and the fact is because we only have two attachments. And so in this case, you'll see an sp hybrid here and sp hybrid here. So a triple bond's a little different. We're going to have two sigmas and one pi, two pi bonds and one sigma bond. And the triple bond's going to have those two pi bonds, and because of that, we're going to have those double bonds. So the way I like to think of a triple is really two doubles and a single bond, which eventually make your hybrid. And that's going to be your sp orbitals, which are going to be with the carbon-carbon, and then obviously your hydrogen here at the bottom. Okay, so your p orbitals are really caused here, making that triple. All right, so sigma and pi bonds are overlapping here. So if you kind of want to visualize a little bit better, you can see the sp2s are sitting right here in the middle. Your hydrogens here are your singles, and then you've got your double bond between the carbons, which actually make your overlapping, pi bonds. Now, sigma bonds contain more energy than the actual overlap. So when you're taking a look at sigma bonds specifically, these sigma bonds really, are a lot stronger than some of the overlap you get from the pi bonds. So normally, just remember sigma is a lot stronger. They usually have that than the overlap from the orbitals. Okay, I'm gonna go into this one part. Okay, so let's talk about bond polarity real quick. So bond polarity has more to do with electrons spending around more time around the area that's more electronegative. So I want you to think of polarity as this unequal distribution of charges because of the fact that these electrons are kind of circulating around. But what happens is that they kind of get shifted towards the one that actually loves taking electrons. And so the more electronegative element has a little bit more negative charge, then the less electronegative has more of a positive charge. So whenever you think of bond polarity, I want you to think about this ability to draw electrons to those atoms. So here's a classic example. Hydrochloric acid, or HCl, is considered to be a very polar molecule. Now in this case, if you notice carefully here, the arrow that we're drawing is towards the chlorine, and chlorine has more electronegativity. So what it does is that it draws those electrons over to the right side. And hydrogen, eventually because of that, ends up getting what they call a partial charge. In other words, a partial positive charge, while chlorine has a partial negative charge. These differences really create what they call bond polarity, because in this case, chlorine is now a little bit more negatively charged than hydrogen. And because of that, there is this effect of unequal distribution of electron charges. And this is basically allows greater what they call bond dipoles. So going back to this idea is that if a molecule is polar, it's going to have this dipole moment. So let's kind of define what dipole real quick. And dipole moment is considered to be Q, in other words, how much partial charge you get for each of the atoms, multiplied by the distance between the positive and the negative poles of the molecule. So obviously the larger that distance is, plus the larger that absolute charge is, the more polar that molecule becomes. And so now you could start really thinking about polarity in terms of distance and also with charges. So if I ask you predict which molecules are going to be more polar than others, you really want to look at those distances and also those charges as well. So if you know that a molecule is polar, you must know that the bonds are going to be polar. In other words, you're going to have that unequal distribution, and you must know the actual shape. So these are the two things you have to memorize in this lesson. So bonds are polar, and then the shapes are going to come from that. So here's an example, again, going back to HCl. HCl has hydrogen here and chlorine, and hydrogen is going to be considered to be, in this case, a partial positive charge because chlorine is pulling on that hydrogen. And so when you do that, it's going to end up getting this arrow going in that direction. Hydrogen here has a positive charge because, again, the electrons are shifting over. And so once we do that, in this case, we know that it's going to be considered polar. The bond dipoles do not cancel, So the molecule has a dipole moment. In other words, it's going to be able to shift towards one side. So for polar molecules consisting of just two atoms, the partial negative charge on the more electronegative atom is always equal in magnitude to the partial positive charge on the less electronegative. So in this case, because the whole thing is considered to be polar, the partial negative charge on them it's going to be in terms of how much it pulls out. It's going to be equal in magnitude, but since the bond dipoles don't cancel, this molecule has an entire dipole. So the way I like to think of this, just to simplify the whole thing, is if one of them is pulling in one direction, the magnitude is usually going to be equal, unless you have another molecule on the other side, so another atom here. So whatever it is here that's getting pulled is going to be equal in magnitude to whatever that partial charge is, just because there's only two of them. Now here's a different situation for carbon dioxide. Carbon dioxide is a linear structure. It's an sp hybrid. And in this case, we're going to talk about polarity again one more time. Carbon in the middle, oxygen on the right and left flanking it. So again, if I'm going to ask you which is more polar and which is less polar, let's talk about the first one. So in this case, we're going to have two pulls. The oxygens are going to pull from carbon on both sides. And then carbon is obviously going to have a partial positive charge, while oxygen is going to have a partial negative charge because oxygen is obviously more electronegative. And in this case, it's going to be considered nonpolar. And the reason why it's nonpolar is because the two polar CO bonds are symmetrical. So symmetrical meaning that if you draw a line straight through it here, they're going to look exactly the same. And what happens here is that they actually cancel each other out. So think of like a tug of war. Someone's pulling from one side, the other one's pulling from the other side. And so because of that, even though oxygen has a higher electronegativity, it's actually not going to have a dipole moment. And because of that, they're actually going to end up, but the bond dipoles are going to cancel each other. So the dipole, the way I like to think of it is how much pull you're actually getting. And because they cancel each other out, the whole thing is actually not going to have a dipole. And so because they don't have a dipole, they are going to be non-polar. Okay, so hopefully that kind of makes sense a little bit. If you want to rewind the tape again, I'm just trying to put it all together. So non-polar means equal pull on both sides. Bond dipoles are canceling because you got one pulling on the other and one pulling on the other, even though they're electronegative, and they are symmetrical. Now here's another example for water. So water here has a little different situation. We have oxygen here more electronegative, pulling on hydrogen on both sides. However, if you take a look at what happens here, oxygen ends up pulling on both sides with a 2- charge. So because it's able to pull those electrons and it's able to take it in, now the problem here is your partial charge here for oxygen becomes only 1, and this only becomes 1, but oxygen actually gets 2. So like the rich get richer and the poor get poorer because they're pulling in from all directions. That's like the best way I can think of. And in this case, we know that it is polar, and they are asymmetrical because what ends up happening is that they're all arranged as central atoms and the dipoles do not cancel. So compared to the other situation where you're pulling on the other sides, like here you're pulling on both tugs. So think of like a person pulling on both sides. This is the stronger person, and what's happening as they're pulling together from left and right, the right hand, they're actually getting even more negative. So now you can't cancel them out, and what that creates is an asymmetric situation where it's not a equal cancel out of dipoles. So this would be considered polar versus the other one, which is nonpolar. So here's another example for BF3, boron trifluoride. And again, you're taking a look at pulls on all three different sides. In this case, because the fluorines are pulling on all three different sides, they basically are considered to be nonpolar. And the reason is because they cancel each other out. This one cancels with this one cancels with this one, so on. So unlike the other situation, this one is an equal distribution of those electrons, and they're symmetrically arranged around the boron, and they eventually cancel out because there's no dipole moment. So this one would be considered a non-polar molecule. Now Cl4 is another situation. In this case, what we have here is another pull situation. However, in this case, we also have 1, 2, 3, 4. And because they're pulling in all 4 different directions, you can predict that in this case is also going to be considered nonpolar because of the fact that they're symmetrical. If you split a line straight through it, you could see they're all symmetrical. And the bond dipoles are going to cancel. So in this case, there's no dipole moment. So aka it's nonpolar. So polarity is really caused by this idea of electron pulls. The more pulls I pull them on different directions, if they're equal, they're going to be considered nonpolar. If they're symmetrical, they're nonpolar. If they're asymmetrical, they're going to be considered polar. So you just kind of have to draw them out and then draw out the electronegativity lines there. All right, so here's another situation where it's a little different. CH3Cl. In this case, we have Cl in there now. Hopefully you can predict what this is going to be. Carbon's in the middle, so again, we're going to focus on the pools here. So chlorine's going to pull on that carbon, and carbon's going to pull on that hydrogen. So what's going to happen here is the more electronegative elements just going to get sucked in into the middle. And so what's going to happen here is obviously we know that this is going to be a asymmetrical pull. And so what you're going to do is that this is going to be a polar because of the fact that the dipoles don't cancel. I can't cancel this out here because they're both going in the same direction. This one's going up, this one's going up. It's all getting sucked up to the chlorine. And because of this, these bonds do not cancel. So this is another great example of a situation where polarity is actually being driven by everything getting pulled to that more electronegative element. Now, here's another example for NH3. NH3 is again going to pull from the hydrogens, and then you've got this extra lone pair here. So now what are you going to do? Well, in this case, what you have is a 3 partial charge, because again, just like the water situation, you're pulling from all 3 directions, and then the nitrogen ends up getting that 3 partial charge. And so in this case, you're going to also get a polar molecule. The 3 H bonds are asymmetrical. They're arranged around this nitrogen, and the dipoles don't cancel. So in this case, again, we can predict what's going to happen based off the fact that they're more electronegatively charged. Okay. All right, and that finishes up that part.